In this lecture, I'm going to expand on our idea of finding the moment of inertia and do some example problems for linear mass densities, surface mass densities, and volume mass densities. So first let's do a linear mass density example. Let's do a hoop, like a hula hoop or something like that. Now let's assume that our hoop has a uniform linear mass density, and remember that we called that variable lambda. So lambda is equal to the mass divided by the total length of my hoop, okay? Now, if you want to take a little chunk of our hoop, so here I've shown the hoop in this kind of weird yellow-green color, right? And then I've shown a little chunk of the hoop in purple right here, okay? So this little chunk of the hoop that's shown in purple has some mass, small mass, delta m. And remember from our previous lecture that that amount of mass would be the linear mass density, the mass per unit length, times the length of our little chunk, okay? Now that little chunk, in this case, our hoop is in a big circle, right, like that. So the chunk would be the arc length of the little chunk of the circle. So it would be some amount delta s, right? And now, of course, the total length of my hoop is just going to be the circumference of my hoop. So L here, the length, would be 2 pi times the radius of the hoop. Now, I've shown that the radius of the hoop is big R, and the total mass of the hoop is big M, okay? So that gives us our delta M, our delta little m, would be big M over 2 pi big R times delta S, the arc length. And that could be written as lambda times delta S. Now delta S, if you shrink down your chunk to be a tiny little thin chunk, then delta S would go to ds, a little differential arc length. Now remember our equation for arc length of a circle. The arc length of a circle S is equal to the radius of the circle big R times the angle subtended by the arc, big theta, right? So that means that ds is equal to r d theta. Now delta m would be equal to lambda times delta s. So as you shrink delta m down to small values, dm would be lambda ds, and then ds is, of course, r d theta. So our dm would be lambda r d theta here. Now remember, for our moment of inertia, the general equation is to integrate over r squared dm, where r is the distance from the axis of rotation to the point in question, and dm is the little differential mass element. So plugging in, all of our little chunks are at the same distance from the axis of rotation. We're assuming that the axis of rotation is shown here, and is at the center of the hoop. So since our radius is fixed for this hoop, and it's big R, then all of our little dm's would be the same distance from the center of the hoop, big R. So that means that little r squared actually is equal to big R squared here, since the radius doesn't vary to all the little chunks. And then dm, we already said, was lambda r d theta. Okay. So you can see via our differential angle here, d theta, that we're integrating over our angle theta. Now we want to integrate all the way around the hoop, so that gives us our limits of integration going from 0 to 2 pi, back where we started. So lambda and big R are constants. I can pull them out front of my integral, and that means that I is equal to lambda big R cubed times the integral from 0 to 2 pi of d theta. Well, the integral of d theta is just theta, and you evaluate theta from 0 to 2 pi, you get 2 pi minus 0, which is just 2 pi. So that means that our moment of inertia is 2 pi lambda r cubed. Now, we could stop here. For example, if there were some numerical value for our linear mass density, like 1 gram per centimeter or something, then we can just plug in that and be happy. But if we're asked to find what our linear mass density is, then we could remember that our linear mass density would be our mass per unit length, which is our total mass divided by our circumference. And if we wanted to plug in for that, we could do that. And so that would be I is equal to, now we have 2 pi lambda r cubed, so that would be 2 pi times m over 2 pi r times r cubed. Canceling out the 2 pi and canceling out the r in the bottom, that gives us our moment of inertia for our hoop, mr squared. Okay? So that's how we can find an example problem here for the linear mass density example of a hoop. Let's do an example of an area mass density, a surface area, okay? So in this case, let's pick on a circular disc, okay? So For an example, they're the record from our last lecture. Okay, this might be an example of a relatively uniform circular disk. So let's again assume that we have some uniform area mass density, so that sigma is some constant value. And sigma, remember, is the mass per unit area of our object. Now in this case, our disk has a radius of big R, just like before, and the total mass is big M. So that means that we could write sigma as being some constant as big M over pi r squared. Now remember that our delta M is going to be equal to sigma times our delta A. So plugging in for that, we would have delta M is equal to M over pi r squared times our delta A. Now let's look at what the area is, delta A, for this little chunk here. Yet again, I've shown the chunk of my mass in this purple square right here. Now, if the origin is here and it's rotating about the center of our circle, then this chunk subtends a change in that radius of dr. So say its length is dr. And its width here would subtend some angle, d theta, right? So if we swing from the plus x-axis to the right-hand edge of our chunk, then we have some angle value there. And then if we keep swinging to the other edge of our chunk, then that might be theta 2. And we could take theta 2 minus theta 1, and that would subtend our little d theta there, okay? Now remember, this is an arc length of a circle, okay? So our chunk, delta M, would have sigma times delta R times delta S. And then as we shrink our delta S down, just like before, then that ds would go to r d theta. So that means that we would have our dm, which is our sigma dA, which would be equal to sigma dr ds, the change in the radius times the change in the arc length, which would be equal to sigma times dr times r d theta. So we could write our dA here as dA is equal to r dr d theta. Okay? And then dm would be times sigma times dA. So now let's plug that into our equation for the moment of inertia. The moment of inertia is the integral of r squared dm. So plugging in for dm here, we would have it being a function of both r and theta. So that means that we've got a double integral here. And so it's the double integral of r squared times sigma r dr d theta. Now r and theta are independent variables, and so we can integrate them separately. So sigma is a constant. We pull it outside of either integral. And then we're going to have the integral over our r part times the integral over our theta part. The integral over our r part would be the integral of r cubed dr, and the limits would be from the center of our circle out to the radius of the circle big R. So we have the integral from 0 to big R of little r cubed dr. Now we're going to integrate all the way around our disk, starting at 0 and going to 2 pi. And so that means that we're integrating 0 to 2 pi of d theta. So those are pretty easy integrals to perform. The integral of d theta is theta, and theta evaluated from 0 to 2 pi is just 2 pi. Now the integral of r cubed dr is 1/4 r to the 4th. And if you integrate evaluate that from 0 to big R, you end up with big R to the 4th over 4 minus 0, which is just big R to the 4th over 4. So that leaves us with our double integral being I is equal to sigma times big R to the 4th over 4 times 2 pi. Now, if you had some, mass density for your chunk, like 1 gram per centimeter squared or something, then you could just plug in for that number. But otherwise, you could plug in for the equation for sigma, which is m over pi r squared. And then that would be multiplied times r to the 4th over 4 times 2 pi. Now things cancel here. The pi cancels out with the pi up top, and r squared cancels out with part of r to the 4th. And that leaves us with mr squared over 2 for our moment of inertia for a circular disk of uniform density. All right, one last example. Let's do something that's three-dimensional in extent. So let's do a cylinder rotating about its long axis as shown here, okay? So the axis runs through the center of the circle on the side, so through the very center, and then all the way down through the bottom. And so it's rotating about that, kind of like a wheel would rotate about an axle through the center. We're going to assume that our cylinder has a uniform mass density, rho, mass divided by volume. Now remember, it's important that you remember your easy geometry, the volume of simple shapes, so that you don't get too confused here. Remember, any upright solid is the area of the base times the height, which here would be pi r squared, because that's the area of the circle at the bottom, times L, okay? So our rho is m over pi r squared L. All right, so that's our mass density. Or if you knew it was made of copper, for example, then you would know that rho is equal to 8.9 grams per cubic centimeter, which might be some constant value. So either way, you're good to go. Now, our little mass chunk here, dm, is now 3D, okay? So if I zoom in and look at what dm would be in cylindrical coordinates, right, then I've got some arc length subtended ds, and some radius subtended dr, and that's just like before on our 2D object. But now in addition to that, I have a height to my chunk, and my chunk would be dz. So to get my volume element dv, I would multiply those three dimensions times one another. dv is ds, dr, dz. And remember that your arc length subtended ds is r d theta. So that means that my volume element is r times dr, d theta, dz. And you might remember this volume element from cylindrical coordinates from your calculus class. Okay, so now that we've got that all worked out, let's go ahead and plug it into our equation and figure out what our moment of inertia is. Okay, so our dm is rho dv, and rho dv is rho r dr d theta dz. So if I plug that into my equation for my moment of inertia, which yet again is r squared, the integral of r squared dm, then I have the integral of r squared times rho r d theta dr dz. Now, each of these dimensions is independent of one another, theta, r, and z, and so I can separate them out and do each integral separately, okay? So I can pull my rho out front, it's a constant, and then I can integrate over dz, d theta, and dr. So here, my origin is at the center of my cylinder, so my z-coordinate, I'm integrating from the bottom of the cylinder to the top, which, assuming it's in the middle, is minus L over 2 to L over 2. So I've got rho times the integral of minus L over 2 to L over 2 dz. Now for my angular coordinate, I'm integrating all the way around the circle, so I'm integrating d theta from 0 to 2 pi. And then my radial coordinate, I'm integrating from the center of my cylinder out to the edge, and the radius of the cylinder is big R, so I'm integrating over the limit 0 to big R of r cubed dr. And the r cubed comes from the fact that I have an r squared here times an r from my volume element. Okay, so if I evaluate those integrals, if I integrate dz, I just get z, and then z is evaluated from minus L over 2 to L over 2. So what I would have L over 2 minus L over 2, which would of course give me L. And then if I integrate d theta, I get theta evaluated from 0 to 2 pi, which just gives me 2 pi. And then if I integrate r cubed dr, I get 1/4 r to the 4th. And then if I evaluate that from 0 to big R, I just get r to the 4th over 4, big R to the 4th over 4. So multiplying all those things together, I have rho times L times 2 pi times r to the 4th over 4. Now, yet again, if rho is some number, I could just plug in from here. But if I wanted to simplify it further, I could. So now I just plug in for rho. Rho is m over pi r squared L, and plug that in. Multiplying it times 2 pi times L and r to the 4th over 4. So that big mess is right here, okay? And then I can cancel a lot of stuff out. The r squared on the bottom cancels out with part of the r to the 4th on the top. The l's cancel, the pi's cancel, and so on and so forth. So when I end up simplifying this expression, I just get m r squared over 2, all right? So there you have it. That's how to find the moment of inertia of a three-dimensional object. Now, here's some moments of inertia for some common rigid objects. There's the hoop, the hollow cylinder, solid cylinder, we already did those. The rod, we did that. Here's the sphere, which we haven't done yet, but we'll cover in a separate lecture. And then here's the long, thin rod that we covered in the last lecture with a moment of the center of mass of 1/12 ml squared. Now, you might be asking yourself, well, what if I don't use some convenient center of mass kind of rotation axis, but I'm rotating about some weird axis? Like, say, for example, I didn't rotate my rod about the middle of the rod, but I rotated it about one end or something. How would that change things, okay? Well, that's where the parallel axis theorem can come in handy. See, you can set up and do your integration with respect to a convenient center of mass coordinate, like we did in the previous 3 examples, and then you can use the parallel axis theorem to offset, okay? Now, this parallel axis theorem simplifies calculations, and it says that if you're doing it through some strange axis, your new moment of inertia I would be equal to the moment of inertia using the center of mass convenient axes that you had, plus md squared, where m is the mass of the object and d is the distance from the center of mass axis to the arbitrary axis. Okay, so that's the parallel axis theorem. Let me do an example for you so that you understand what I'm talking about. Let's take that rod that we had before. Remember that in the previous lecture, we found that the moment of inertia for a rod rotating about its center is 1/12 ml squared. Okay? Now, let's say that instead of rotating about its center right here, we moved it over to the edge so that the new rotation axis is shown and indicated here. That would mean that d would be the distance from the old axis, the center of mass axis, to this new weird axis. That distance is L over 2, right? D is 1/2 L. So d squared would be L squared over 4. So you would take this 1/12 ml squared, which is the center of mass moment of inertia, and then add to it m times L squared over 4. And when you do that, you end up with 1/3 ml squared, okay? So that's how to use the parallel axis theorem if your axis isn't located in a convenient spot. All right, well, I hope that helps, and I hope you understood it, and I'll see you in class.